Let's solve problem 4.42 for Microelectronic Circuits, 8th edition by Sedra and Smith. So we have two circuits, and we're going to use the constant voltage drop method, which is VD equals 0.7 volts. You're going to use that model to find the voltages and currents indicated. So when we have two diodes, it's best to just make a guess of which one is on, which one is off, if both of them are on or off. I usually just start by guessing that one is on and one is off. Where on is being forward biased, so it behaves with the voltage drop of 0.7 volts. And then the other one is off or reverse biased, so it acts like an open circuit. So we're going to start by assuming D1 is on and D2 is off. So since D1 is on, it's going to have the 0.7 volt drop. So let's get started with circuit analysis. So one of the things we want to find is V, and once we find V, we can solve for I. So according to our current assumptions, if D2 is off, it behaves like a giant resistor, an open circuit. It's not seeing any of that voltage. It's consuming all the 2 volts. But that means V would be equal to 1 minus the voltage drop across D1, 0.7 volts, which is equal to 0.3 volts. Now this may look good, but let's check if this is consistent with our assumptions. D2 is seeing 2 volts from the anode and 0.3 volts from the cathode. But we stated that D2 is off. However, this doesn't really make sense because we're going from high to low. So this doesn't make sense. If we're going from high to low, 2 to 0.3, D2 should definitely not be turned off. So let's switch our assumptions. We'll now say D1 is off and D2 is on with VD equals 0.7 volts. So now because D1 is an open circuit, we're going to solve for V using the drop across D2. So 2 volts minus 0.7 volts equals 1.3 volts. And let's verify for D1. So we have 1 volt and 1.3 volts. So sure enough, this is going from low to high, 1 to 1.3. So this diode is indeed reverse biased. Okay, now let's continue with the circuit analysis. We can solve for I using just simple nodal analysis, right? We'll subtract 1.3 volts from 9 volts. Divide that by the resistance of 2 kiloohms. That is equal to 5.15 milliamps. So we had to just double check our assumptions, make sure everything looks right, but this first problem is solved. Let's move to the second circuit. All right, so here's our second circuit. And let's just start with our assumptions. I'm going to start by assuming D1 is on and D2 is off. So D1 is on, meaning it experiences that voltage drop of 0.7 volts. D2 is off, so it behaves like an open circuit. So this 2 volts is just being consumed by the diode. We're not concerned with that. So let's start to solve for V. So if I'm traveling this way, starting at the 1 volt, it would be 1 plus the voltage drop across D1, which is 0.7 volts, and that is equal to 1.7 volts. Let's check with diode D2 to make sure that this actually makes sense. So this is what D2 looks like, right? So currently we're saying that there's 1.7 volts here from the anode, and from the cathode, there's 2 volts. So we're going from 1.7 to 2, low to high. So D2 is reverse biased, and therefore it is indeed off. So now we can just solve for current. I is equal to 9 volts minus the value of V, 1.7 volts, divided by 2 kiloohms. That is equal to 3.65 milliamps. So we have solved this problem.